Irreducible elements are the building blocks of elements in domains in ways similar to how prime numbers are the building blocks of integers. What we're going to look at now are some properties of rings that guarantee that any number can be factored into irreducibles, and we're also going to describe the condition of that being of that factorization being essentially unique. So the first question that we have to deal with is it even possible to express an element of your ring as a product of irreducible elements? And while this isn't always the case, it turns out to be true for Noetherian rings. So Theorem 128 says, let R be a Noetherian domain any element of R can be written as a product of irreducibles, of irreducible elements. I should specify here that the element has to be non-zero and a non-unit. So if you're Noetherian, then every element can be written as a product of irreducible elements. And let's see how the proof goes. So let's let R be a Noetherian ring, Noetherian domain, I should say. First, we will show that every element of R can be written as a product of some irreducible element and some other ring element. And the way that this is going to go is the following. So let's let A be an element of R. If A is irreducible, then we're done. Because then A is equal to itself, and so it's the product of one element together, so A can be expressed as a product of irreducible. So otherwise, let A be a non-zero, non-unit, and not irreducible, or in other words, reducible. So the basic idea behind this proof is the following. We can write A equals B times C, where B and C are both non-units. And in fact, I want to write this as B1 and C1. And then if B1 is so B1 is a non-unit, and if B1 is an irreducible element, then we've proven our first step. Remember, our first step is to prove that A is a product of some irreducible element and some other element of the ring. If B1 is not an irreducible element, then that means that we can write it as a product of two non-unit elements, and so forth and so on. So this is the basic idea. We're going to keep looking at this first factor, B1, B2, B3, and if possible, if it's not irreducible, we're going to keep splitting it up into parts. And the Noetherianness of the ring R is what's going to guarantee that this process has to eventually stop. And that's the idea behind the proof that we're going to do. Let me go ahead and start this sentence over. So what we're going to do to make this process precise is we're going to recursively define a sequence of elements B0, B1, B2, etc. As follows. B0 is simply going to be A, and then for all k's greater than or equal to 0, we're going to set bk to be equal to bk plus 1 times ck plus 1, where bk plus 1 is a non-unit and ck plus 1 is a non-unit if possible. So we're starting with a non-unit, we're starting with A, which means that we can always write it as a product of some non-unit with something else. A is equal to A times 1, for example. But we're going to choose a product in such a way that B is never a unit and C is not a unit if it's possible to choose it that way. Basically, if bk is reducible, then bk plus 1 and ck plus 1 will not be units. But if bk plus 1 is irreducible, or if bk is irreducible, then bk plus 1 will not be a unit, but ck plus 1 will be. Okay, so now we're going to consider the chain of ideals we have that the ideal generated by A is contained in the ideal generated by B1, because B1 divides B0, which is A. B1 is contained in the ideal generated by B2, because B2 divides B1, which is contained in the ideal generated by B3, etc., etc. So we have this ascending chain of principal ideals. Now, our hypothesis is that R is Noetherian, which means this ascending chain eventually ends. Or stabilizes, I should say. Since R is Noetherian, this chain eventually stabilizes. That is, there is some number n with the ideal generated by Bn equaling the ideal generated by Bn plus 1. Therefore, we have that Bn plus 1 belongs to the ideal generated by Bn, and so it equals to little r times Bn for some little r in the ring R. But we also have that Bn plus 1, which is equal to Rbn, and by construction, Bn is equal to Bn plus 1 times Cn plus 1. Now, you'll notice that Bn plus 1 is a factor of both the left and the right-hand side of this equation. So by cancellation, we have that 1 is equal to R times Cn plus 1. Therefore, that tells us that Cn plus 1 is a unit. And remember, we only chose the C to be a unit if it was not possible to express the previous B, Bn, as a product of two non-units. So thus, it is not possible to write Bn as a product of two non-units. Therefore, Bn is irreducible. Then finally, we have that since the ideal generated by A is a subset of the ideal generated by the Bn, we have that A is equal to Bn times C for some C in the ring R. So thus, every non-zero non-unit of R has an irreducible element as a factor. Right. So now that we've shown that every non-zero non-unit element of R can be written as the product of some irreducible element with some element of R, we can move on to show that every element of R can be written as a product of irreducible elements. We're going to follow a similar argument pattern to the first one, but we're going to use what we proved in the first paragraph to construct our sequence of elements in the second one. So let's let A, an element of R, be a non-zero non-unit, and let's define a sequence C0, C1, C2, etc. as follows. So we're going to let C0 equal A, and for all k greater than or equal to 0, we're going to let ck equal bk plus 1 times ck plus 1, where bk plus 1 is irreducible if ck is a non-unit. By the previous paragraph, any non-unit can be written as the product of an irreducible element with something else, and so we are always going to choose a factorization of ck that allows that, so long as ck is a non-unit. Now again, we have the chain of ideals that goes A, which is contained in C1, because C1 divides C0, which is A, which is contained in C2, which is contained in the ideal generated by C3, etc. And this has to eventually stabilize. And so that means that we have that the ideal generated by Cn is equal to the ideal generated by Cn plus 1 for some n. Now we're going to follow, again, a similar sort of argument that we had before. So this means that Cn plus 1 has to be equal to Rcn for some r, for some little r in R. And so we have that Cn plus 1 is equal to Rcn, which is equal to R times C we have that Cn plus 1 is equal to R times Cn, and Cn is equal to Cn plus 1, or Bn plus 1 times Cn plus 1. And again, by cancellation, we have that 1 is equal to R times Bn plus 1. So in particular, this means that Bn plus 1 is a unit, hence not an irreducible element. Well, we always picked our B elements to be irreducible if the previous C was a non-unit. So if this bn plus 1 is a unit, then it's not irreducible, which means that Cn is a unit. Therefore, what we have is that A is equal to, well, I'll do the first couple of steps of this. It's equal to B1 times C1, which is equal to B1 times, now C1 was equal to B2 times C2. C2 is equal to B3 times C3. And so following this out, we get that A is equal to B1, B2 up through Bn, Cn. But now Cn is a unit. And so we can write this as, let me write this as Bn minus 1 times Bn times Cn. Now all of the B1s through Bn minus 1s by hypothesis are all irreducible elements. And the product of an irreducible element with a unit is also an irreducible element. This is easy to see. So in other words, any associate of an irreducible element is an irreducible element. Thus, we have that A is a product of irreducible elements. So in a Noetherian ring, any element can be written as a product of irreducible elements. All right, so that's great. It tells us that Noetherian domains have a minimum amount of good properties when it comes to factorization. However, it turns out that simply being Noetherian is not enough to get us all of the factorization properties we would really like. Let's look at an example that we saw in a previous section. So let's let R be the ring Z adjoining the square root of -7. And remember, the elements of this look like A plus B times the square root -7, where A and B are integers. We already saw that in this ring, prime and irreducible elements are different. It turns out that R is Noetherian. The easiest way to note that is to note that R is actually isomorphic, and this is a good exercise. It's isomorphic to the factor ring Z adjoin X, quotiented by the ideal X squared plus 7. And we know from previous sections that Z is a principal ideal domain, hence Noetherian. We know that a polynomial ring over a Noetherian ring is Noetherian, and we know that a factor ring of a Noetherian ring is Noetherian. So the ring R that we're looking at is Noetherian. It satisfies the ascending chain condition, and all ideals of R are finitely generated. We have that every element of R can be expressed as a product of irreducible elements. However, this is not unique. This factorization is not unique. Let's consider the element 8 in this ring. On the one hand, 8 is certainly equal to just 2 cubes, so 2 times 2 times 2, but we computed in a previous example that 8 is also equal to the product of 1 plus the square root of -7 times 1 minus the square root of -7. And it turns out that both of these elements are also irreducible. So these are irreducible, and all these elements are irreducible. Let me actually write it out as 2 times 2 times 2. All these are irreducible. However, this factorization is highly non-unique. As we see here, 8 can be factored in at least 2 ways, very distinct from one another. These 2 factorizations don't even have the same number of factors involved, and the factors that they do have are very different from one another. So this ring does not have all of the nice properties that we like to use about factorization in, say, the integers, or as it will turn out, polynomial rings over a field, or over the integers. So we want to define some sort of stronger notion of factorization that will cut out rings like this that don't factor elements well, and really focus on those rings that have good factorizations. And that's where our next definition comes in. So definition 129. A domain R is called a unique factorization domain and we often abbreviate this as UFD, if every non-zero, non-unit element A in R can be factored as A equals B1, B2, up through BR, B little r, where the BI are irreducible. Elements of R. Furthermore, we need something more than this. This would be a factorization domain if we wanted to say that, just saying that every element can be written as a product of irreducibles, like we showed all Noetherian domains are. But we want this to be a unique factorization domain. So furthermore, we want that factorization to be unique up to reordering and associates. That is, if A equals C1, C2, up through CS is a factorization of A into irreducibles, then R has to equal S. So the number of irreducible factors in a factorization has to always be the same. And the CI may be reordered so that each CI is associate to BI, or I should say, so that for each I. So that for each I, CI is associate to BI. So we don't need the factorizations to be absolutely unique. That's basically never going to be possible. Reordering makes sense. Associates also are a very natural thing to do. So for example, if we look at the integers z, which are definitely a unique factorization domain, we will note that if I look at the element 12, one factorization of 12 would be 3 times 2 times 2. That's a factorization of 12 into irreducible elements. Remember that in the ring Z, irreducible elements and prime elements are the same. And we could also write 12 as 2 times 3 times 2. So, of course, the order of the factors can be expected to change. We can't expect the ordering to be unique because we're in a domain, hence we're in a commutative ring. But furthermore, we could have a factorization like this. -2 times -3 times 2. Now, -2 and -3 are irreducible elements of the integers. They are associate to the elements 2 and 3, and as we mentioned earlier, associates of irreducible elements are themselves irreducible elements. So we can't expect rings to be any more unique in their factorization than this. We always have to allow reordering of the elements, and we always have to allow replacing a couple of the elements by associates in a way that that cancels each other out. Like here, where I change two separate factors to their associates. But we're not allowing anything more. So a unique factorization domain is a domain where we're requiring the factorizations of any non-zero, non-unit element to be as unique as could possibly be reasonably expected in a domain. And this is the type of factorization that we see in the integers. It's the type of factorization that we're used to working with actually when working with polynomials. We know polynomials factor, and we've often sort of implicitly used the fact that they factor uniquely. So we have this definition. It's sort of a long one, but it basically says that factorization into irreducibles in the ring behaves like factorization of numbers into prime numbers and the negatives of prime numbers. So for a few examples, we had that Z is a unique factorization domain, as just mentioned. We will see in a while that f of x is a UFD for any field. In fact, Z adjoin x is also a UFD. We have that Z adjoin the square root of -7 is not a UFD. Now, this shows in particular that the property of being a unique factorization domain does not persist when moving to factor rings, because we saw earlier that this ring Z adjoin square root of -7 is a factor ring of the ring Z adjoin x, but while Z adjoin x is a unique factorization domain, Z adjoin the square root of -7 is not a unique factorization domain. Now, many rings, as we see here, that we deal with are unique factorization domains, but not all of them. Now, we defined the unique factorization domain in terms of irreducible elements. It turns out that in unique factorization domains, irreducible elements and prime elements are the same. That's the next thing we're going to prove. It also turns out that we could have defined unique factorization domains in terms of prime elements rather than irreducible ones. Part of the reason why we define it in terms of irreducible elements is that irreducible elements are often a little bit easier to work with. There are fewer things to check. You just have to check that this one element can't be broken up into smaller ones, rather than the primality condition, which requires you to check all possible ways that an element can divide a product of two other elements. All right, so let's do Theorem 130. Theorem 130 states that in a unique factorization domain, all irreducible elements are prime. We already know that all prime elements are irreducible, and Theorem 130 says that in a UFD, the inverse is also true. So in a UFD, irreducible elements and prime elements are the same. Let's do this. Let's let R be a unique factorization domain and an element of R an irreducible. So now let's let B and C be in R such that A divides BC. So that means that there exists an element D in R such that A times D is equal to B times C. So now A is an irreducible element, which means that A appears in the factorization, the irreducible factorization of the product AD. D can be expressed as some product of irreducibles, and therefore A times D is equal to A times that product of irreducibles, and therefore A appears in the irreducible factorization of AD. Therefore, that means that A must appear in the irreducible factorization by irreducible factorization, I mean the factorization into irreducibles. A must appear in the irreducible factorization of the product BC. Now, since a factorization of BC is given by a product of the factorizations of B and C, this means that A must appear, well, I should say up to associate, in the factorization of B or C. Thus, A must divide B or A must divide C. So that shows that A is prime. Just really quick, I want to write out in symbols the main thrust of the argument here, just for clarity. So we have that D can be written as D1, D2, up through dr, let's say. We have that B can be written as B1, B2, up through Bs, and C can be written as C1, C2, up through Ct, where Rs and T are integers. The Di, Bi, and Ci are all irreducible elements. So that means that since AD equals BC, then whatever this element is, this element AD, which can also be written as BC, has two factorizations that we have written down. We've got A times D1, D2, up through dr. B times C can be written as B1, B2, up through Bs, then C1, C2, up through Ct. So what we have is that whatever this element is, we have two factorizations of it, the one given on the left and the one given on the right, because all of the symbols involved here are now irreducible elements. Since R is a unique factorization domain, these two factorizations must be essentially unique, meaning that all of the elements, there must be the same number of elements on both sides, and after reordering, each element on the left must be associate to its corresponding element on the right, which means that if I pick out any irreducible element on the left, such as, for instance, A, it must be associate to some irreducible element over here on the right-hand side. So it must be associate to either a BI or a CJ, one of the others. In either case, it divides B or C. So this is the idea. In a unique factorization domain, if you have two products of irreducibles that are equal to each other, then those irreducibles must be associate to one another after some reordering. All right, so in a UFD, all irreducibles are prime. Now, we've actually already seen this condition of irreducibles being prime. We know that that happens in a principal ideal domain. So principal ideal domain has the property that all irreducibles are prime. That's going to be useful to us in a moment when we prove that UFDs and PIDs are related. One of them sits inside the other as classes of rings. Now, because in UFDs irreducibles are prime, it's the case that in a UFD, every element can be factored into irreducibles. By Theorem 130, all irreducibles are prime, so that means that every element can be factored into prime elements as well, which is actually a priori a stronger statement because all primes are irreducibles, but not vice versa in arbitrary rings. However, we can use this to prove that UFDs could be defined or characterized by prime elements rather than irreducible ones. So, a commutative domain R is a UFD if and only if every non-zero, non-unit element of R is a product of prime elements of R. Now, you'll notice that this definition doesn't require us to check any sort of uniqueness. The uniqueness will actually simply come from the prime condition on the elements that we're checking. So if you're looking at a ring and you can show that every non-zero, non-unit element can be written as a product of prime elements, you don't have to check any sort of uniqueness or anything. That ring is already a UFD by Theorem 131 here. Okay, so as I said, going one direction is an immediate consequence of the definition in Theorem 130. So if R is a UFD, then by definition, every element can be written as a product of irreducibles. Sorry, every non-zero, non-unit element can be written as a product of irreducibles, and by Theorem 130, those irreducibles are prime. So that proves the forward direction, that if R is a UFD, then every non-zero, non-unit element of R can be written as a product of prime elements. So let's go the other way. So now let's suppose that every non-zero, non-unit element of R is a product of prime elements. What we have to show now is that R is a UFD. We already know that it's a domain. I'm being redundant here. I say commutative domain. All domains are commutative. So we already know that R is a domain, and so we need to show that R is a UFD, meaning that we need to show that every element can be written as a product of irreducible elements, and that that factorization is essentially unique. Now, we have that. We can let A, B, and R be a non-zero non-unit. By hypothesis, A is equal to the product P1, P2, up through PR for some prime elements PI. But all prime elements are irreducibles. So since all primes are irreducible, this is a factorization into irreducibles. All right, so this shows that every element of R can be written as a product of irreducible elements. Now we need to check the uniqueness part. And here's where we need to be a little bit careful, because the uniqueness part of the definition of the UFD says that if I have any two factorizations into irreducible elements, then they have to be the same up to reordering and associates. So we're going to handle that by assuming that A has another factorization, but we can't assume that that this other factorization is into prime elements, only into irreducible ones, and we'll show that that factorization has to essentially be the same as the one that we started with, as the P1 through PR. So we can let A equals B1, B2, up through BS be a factorization of A into irreducibles. At this point, we don't necessarily know that that the B's are going to be prime elements. Okay, so what we're going to do is we're going to prove that these two factorizations are unique, or are essentially the same, sorry, that the factorization is unique by using induction on R, the number of elements required, the number of prime elements required in a factorization of A. So we use induction on the number R, the number of prime factors in a prime factorization of A. So the base case is if R equals 1, then A is equal to P1. So in fact, A is prime. Now A equals this factorization B1, B2 up through BS, where the B1 through BS are irreducibles. So that means that A divides one of the BI, because A itself is prime. Sorry, I'm getting ahead of myself. I'm looking at the inductive step, which is harder. In this case, we have that A is irreducible, since A is prime. So we must have, in fact, that S is just equal to 1, because since A is irreducible, it can't be the product of more than one non-unit elements. And so A is equal to B1. So we have that P1 equals B1. So in fact, in this case, when R is equal to 1, the factorization is completely unique. There's no reordering to be done, and the P1 and the B1 are not just associates, they are actually equal to each other. So the case R equals 1 when A itself is a prime element is pretty immediate like that. So now we're going to step up to the inductive step. So let's suppose that R is greater than or equal to 2, and that the factorization into irreducibles of any element which is a product of R minus 1 prime elements is unique. Where here unique means up to reordering and associates. Now, we have that that A is equal to P1, P2 up through PR, but we also have that A is B1, B2 up through BS. So now we have that PR divides A, so that means that PR divides the product B1 up through BS. Since PR is prime, we have that PR divides BK for some K. Therefore, BK is equal to PR times U for some U in R. But what the thing that we know about BK, we don't know it's prime, but we do know it is irreducible. So since the BK is irreducible, we have that U is a unit, because PR is certainly not a unit. So in particular, this means that PR and BK are associates, which is good. Good for us. It gets us partway there. So if we replace BK with UPR, we get the following, which I'll do on the next slide. We get that P1, P2 up through PR is equal to B1 up through BK minus 1 times BK, but BK is equal to U times PR times BK plus 1 up through BS. So now you'll notice that we have the element PR appearing in both sides of this equation. So by cancellation, we have that P1, P2 up through PR minus 1 is equal to, we cancel the PR and we're going to be left with UB1 up through BK minus 1, BK plus 1 up through BS. So now this left-hand side is an element that is expressible as a product of R minus 1 primes. And this right-hand side, when we group up the U and the B1 together, is a product of irreducibles. So we can use induction at this stage. By induction, we had that the factorization of anything that could be expressed as a product of r minus 1 primes is unique, so that's what we have here. So by induction, we have that r minus 1 is equal to s minus 1, which notice is the number of elements, the number of factors on the right-hand side now. By induction, r minus 1 equals s minus 1, and the elements Pi are associate to the elements UB1, B2, up through Bs in some order. The extra factor of U right here doesn't really change anything, because if you're associate to a unit times something, then you're associate to that thing. So, therefore, we have that R equals S, and since we previously had that PR is associate to BK, because this list doesn't include the BK, so since PR is associate to the BK, we are done. We've shown that the two factorizations P1 through PR and B1 through BS, first of all, have the same number of elements because R equals S, and that all of the P's are associate to the B's in some order. Thus, R is a unique factorization domain. We can use this fact that the unique factorization domain condition can be defined in terms of primes in order to show that every principal ideal domain is a unique factorization domain. So that's Theorem 132, which tells us that every principal ideal domain is a unique factorization domain. And the proof is really just a combination of a bunch of the theorems that we've had so far. So let R be a PID. Then R is clearly Noetherian by Theorem 130. By the theorem that told us that Noetherian rings are characterized by having all ideals be finitely generated, which I've lost the reference for just now. So R is Noetherian. So that means that every non-zero, non-unit element of R can be factored into irreducibles. By Theorem 128. So Theorem 128 says that if you're in a Noetherian ring, then every element can be factored into irreducibles, but not necessarily uniquely. But by Theorem 123, irreducible elements in a PID are prime. So that means that every non-zero, non-unit element of R can be factored into primes. So, by Theorem 131, R is a unique factorization domain. So this gives us a containment of domains. So all PIDs are contained in UFDs. Every PID is a UFD. The question can reasonably ask whether the containment goes the other way. Are principal ideal domains and unique factorization domains simply the same thing? The answer is no. They are not the same. The example that we will eventually have is the polynomial rings over the integers. There are, of course, lots of examples, but this is the easiest one to get. So this is a UFD, but not a PID. For instance, the ideal generated by 2 and x in this polynomial ring is not principally generated. There is no single element which generates this ideal. And so here we have a UFD, but not a PID. We can see that this ring is not a PID quickly. This example works. Showing that it's a unique factorization domain is actually going to take a little bit of work. We're going to, over the next few sections, look at how we can compare the unique factorization of a coefficient ring with the unique factorization of a polynomial ring over that ring.